Okay, so we had this question in Mathematize about the slope of the secant line, and the slope of the secant line depends on 2 points, but what happens when one of the points gets very close to the other point for this function, y equals x squared? The slope seems to get closer and closer to, what did people say? Ooh, all sorts of different values. 0, 1, 2, 3, 4, 5, 6 seems slightly more popular, and the correct answer is indeed 6. The correct answer is 6. The way you were supposed to see that was from the animation. So the animation is the guide here of what is going on. Let's look at it a little bit more closely. Let's slow this down so we can look at what happens. So here, things are, the slope is 7. Let me make this a little easier to see. Okay. So here is the interval from 3 to 4. So a equals 3 is the middle point. B equals 4 is the other point, and the slope is 7. And as you get closer and closer, you go 7, and then you're at 6.5, and then you're at let's say 6.2, and then you're at 6.05. And as you get closer and closer, eventually, if you're exactly there, it's undefined, but right before you get there, it looks like it's getting really close to 6. And you can do the same exact game from the other side. So if you start over here, the slope is 5, and then as you get closer and closer to the 1 point, the slope values go up, 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 5.8, 5.9, 5.99, and then Desmos says undefined, but we're 5.99, we're getting really close to 6. So the slope here is 6. And the way you could check that the slope is 6, you can make a line of slope 6. So here is an equation of a line of slope 6, and it's going to go through this point. And if I'm right that the slope is 6, then the green line should be getting closer and closer to that red, what I think is the tangent line. So let's see, is the green line getting closer to the red line? Yes. And also another way to tell is if you zoom in, the original function should be kind of look more and more like that red line. That red line should approximate, it should cover up the black line quite well. And it does. So the answer is 6, the slope is 6, and we just saw visually why. In the rest of this class, we're going to learn why using algebra. So we're going to do it with algebra as well. But this is the main core concept for calculus that we're doing, is this idea of the tangent line approximating the real line, if the real function. Are there any questions about this idea? This is a good time to ask. We're going to go deeper and deeper right now. So like right now is conceptually sort of the simplest right now, which I know there's already a lot of moving parts. Okay, so let's jump into the algebra. We're going to repeat this idea and figure out why using algebra it works. So last class we sort of did it when a equals 1. We found by algebra that it was 2. And today we're going to do it for all the other values. And we're going to start on this page, page 431, which is the idea of the difference quotient. The difference quotient. And the difference quotient is really the average rate of change on some interval that is equal to the slope of the secant line that I just showed you. So this is the slope of the secant line. The secant line. So it's the slope of that green line in Desmos. And you have to specify what are the 2 points you're going through. And we're going to use the letters x and h to represent those. So x is one of the points, and x plus h is the other point, b equals x plus h. So this is the slope of the secant line from x to x plus h, from x to x plus h. And here is a little picture of what it looks like. Here is the base point at x, and here is the other point at x plus h over here. So that's the notation we're using. X represents where we are. So in the example we just did, x was 3, and x plus h represents the other point. H is how far apart they are. The secant line is this line connecting the 2 points that looks like this. It's supposed to be a straight line. This is the secant line. Okay, let me actually just draw the arrow. This is the secant line. That's the secant line, right? So the average rate of change of the function is the slope of that green line. That's the slope of the secant line. And that's from x to x plus h. Okay, so we would like to know what this is getting close to when x and x plus h gets close together, when h is getting close to 0. That's what we're going to do. And here is the formula for the slope, rise over run. This is the rise. The run here is h. Rise over run gives us the slope, and you can also see it visually here and here, right? So that is the function. The function and the slope of the secant line. Any questions about the setup so far? We're about to do an example where we're going to do the squared function, but this is good time for questions. It's a lot of notation all at once. Okay, if it's not enough notation, we'll add more notation. So they call this thing, they call it the DQ. That stands for Dairy Queen. No, it stands for difference quotient. Difference quotient. So DQ stands for difference quotient, and it just means what we just saw. It's the average rate of change from x to x plus h. That's what we mean when we say the DQ. And it has this formula, which is just the slope formula for our particular setup. Let's figure out what this is for our x squared function, and that is on the next page. F of x equals x squared, determine the difference quotient. So we would like to know the DQ equals what? And the DQ, remember, is just the same thing as the average rate of change on x to x plus h, or also known as the slope of the secant line here. Slope of secant from x to x plus h. Okay, so it's going to involve the two numbers x and x plus h. We're going to figure out what it is. The general formula that is always true is f of x plus h minus f of x divided by h. That's the general formula. And in our particular case, we're dealing with the function, which is the x squared function. So in our case, this is x plus h squared minus x squared divided by h. Okay, and that's a perfectly good formula. In fact, this is the formula that I put into Desmos where Desmos was calculating the slopes. But this formula has a problem. The problem happens when h equals 0. So there is an issue, oh, that's not how you spell issue at h equals 0. When h equals 0, you're dividing by 0, and that is bad. Because h equals 0 is exactly what we're interested in. We want the 2 points to get close together. So we want the point x to x plus h to get as small as possible. We really are interested in h equals 0, and the whole thing is a disaster at h equals 0 because of the divide by 0. But if you look carefully, the top is also 0 at h equals 0. When h equals 0, the top is also 0. So when h equals 0, this whole thing is a 0 over 0 situation. The whole reason of doing limits and doing the 0 over 0 limits that we saw in chapter 10 was to answer the question, what happens to the difference quotient in this situation? That's the only reason to do limits. The whole point is to be able to answer this question and find the value of the slope. Where Desmos says it's undefined, we're going to figure out that the answer was 6, or whatever it is. So this is a great situation. That is the formula for the difference quotient, but we are going to simplify it. And we're going to simplify it in the right way to make the 0 over 0 go away. We're going to try to simplify it so that we get a formula where you can easily see what is going to happen when h goes to 0. And the observation algebraically is that we have a difference of squares. There's a question here first. Yeah. Okay, let me do it. So you're going to get x plus 0 squared minus x squared, right, when h equals 0. And x plus 0 squared is x squared. X squared is x squared minus x squared is 0. So it will, and in fact it will always do this, right? Because when you plug in h equals 0, you get f of x minus f of x. It always is going to be 0. Yeah, maybe I did it a little quickly because it's always a 0 on top as well. That's a fantastic question. Okay. Yeah, very, very good to know. Other questions or comments at this point? Okay, so let's simplify it. This is the trick we saw last class. You have something squared minus something else squared. That's a difference of squares. So if you notice the difference of squares, you can write this whole shebang, x plus h minus x times x plus h plus x. That is the top of the fraction there. Because it's a difference of squares, you can write it in this way. This is like a nice factoring. The bottom is unchanged. The bottom is still h. But now there is even more simplifying that happens. You have x plus h minus x. X plus h minus x. So you're adding an x, and then you're subtracting an x. You might as well have done nothing. Those two x's cancel out. And you are left with h times something. What is the something? Well, the something also simplifies because you have x plus an x. You start out with one x. You add on another x. That's 2x. 2x plus h. So there's the top. The first thing just simplifies down to h. The x's cancel each other out. In the second thing, the two x's come together to make 2x. That was the second thing. The bottom is still h. Okay, but now we notice another nice miracle. We have an h on the top and an h on the bottom. those also cancel out. So h on top, h on the bottom. You multiplied by h, you divided by h. You might as well have done nothing. That's what canceling out means. So the final answer, this whole thing simplifies down to the formula 2x plus h. 2x plus h. So what have we done? We've calculated the difference quotient, this slope of the secant line, and we have figured out a nice formula, 2x plus h, where the formula is really nice. You can plug in any x and h value you want, even though originally it was a 0 over 0. And that is the skill we learned in doing limits, is how to make these 0 over 0s go away. We're going to see why that, making the 0 over 0 go away, why that's important when we do the limit as h goes to 0. Okay, that's part A. We're about to do part B. Any questions about any of the algebra or what we're doing here or why we're doing it? I mean in the math class, about part A. Okay, let's do part B. Part B says, figure out what's going on when x equals 1 and h equals 1/10. When x equals 1 and h equals 1/10, then dq is 2 times 1 plus 1/10. So in general, it's 2 times x plus h. If x is 1 and h is 1/10, 2 times 1 plus 1/10, that is 2.1. Okay, so it's 2.1. So what? What does this 2.1 represent? This 2.1 represents the slope. This is the slope of the secant line, of the secant, from 1 to 1.1. Right? Because in general, it's the slope of the secant from x to x plus h. So if x equals 1 and h equals 1/10, then it's 1 to 1.1. So that is what we've calculated. The slope from 1 to 1.1 is 2.1. We have this nice formula, 2x plus h. And we can check that it's true. Let me freeze this for people still copying. But you can check that it's true on Desmos. Let's put in a equals 1, and b, I want b to be 1.1. Will it let me do that? 1.1. So there you go. There's what we're looking at. Let's turn off the tangent line from before. That is what we did. We just calculated this. And in Desmos, we had this kind of like gross way to do it, just like brute force on a computer. But now we have a nice algebra way to also get the same answer. So we're calculating what the slopes of the secant line are, just like Desmos was doing. All right. Any questions or comments about what we're doing here? Okay. So what is next in the notes? In the notes, they say we calculated the difference quotient for x squared. Was there a question here? Yeah, go ahead. The which? The answer was, before the answer was 6, that was when x was 3, right? In part B of this question, x equals 1. So right now, I'm looking around x equals 1. This is a very important point. If you look around x equals 1, that's when you get 2.1. So from 1 to 1.1, the answer was 2.1. In the question we did at the beginning of class today, that was at x equals 3, and that will come up later. So soon we're going to do it for any value. In the notes, they went with 1. That's what I'm doing. That's why I did 1 this time. By the way, this x equals 1 is what we did last class, at the very end of last class. And I will come back to x equals 3 later. Yeah. OK. So in the notes, we just calculated the difference quotient. We just calculated the difference quotient for f of x equals x squared. That's what we just did. In the notes, they say, why don't we calculate the difference quotient for a whole bunch of other functions too? Right? So they calculate the difference quotient for x squared. They do it for square root of x. They do it for 1 over x. They do the difference quotient for like every function possible. But I want to show you guys why we care about the difference quotient. What is the point of the difference quotient? The only reason is to do the limit of the difference quotient and get the slope. So in the notes, they say, the reason will become clear later. The reason will become clear later. And I think that is bullshit. The reason should become clear now. We're going to show you the reason now, okay? So what it's going to involve skipping around in the notes a little bit, because the notes, first they do x squared, then on the next page they do square root of x, then they do 1 over x, then they do the absolute value function. And then only then do they eventually get to doing the fun thing of doing the limit and the slope of the tangent line. But I'm going to skip ahead here, and so I'm going to hijack this page 437. On page 437 is a blank page, and I'm going to hijack this page and make a nice little table of what we're doing to try to organize my thoughts. And then the rest of the class, I'm going to be skipping all over the notes. I'll try to tell you where I go and when I go let's do it. So what we just did already, we computed the slope of the secant line, slope of secant, and that was from x to x plus h. That is what we did. This was called the dq, and we computed what that was for the function x squared. So I'm making a table. The table looks like this. Here's the function x squared. We worked really hard. Let me make this a different color. So you know this is the top row. We worked really hard to calculate that this was 2x plus h. So that's what we've done so far. We've calculated that the dq for x squared is 2x plus h. For a general function f, no matter what the function f is, this dq is always f of x plus h minus f of x divided by h. And we simplified it, and that's how we got 2x plus h. So that's what we've done so far. What I want to get to is the next row of the table, which is not the slope of the secant line, but the slope of the tangent line. The slope of the tangent line. And I want to do that at x equals 1. That's going to be the next line. We did this a little bit last class. We said the slope of the tangent line should be 2. And we did it at the warm-up problem today. We did it at x equals 3. But we're going to fill in this table with what happens at x equals 1. And in general, what always happens, the slope of the tangent line is always just the limit of the slope of the secant line. So we're going to do the limit as h goes to 0 of the dq. Yeah, okay, let me write it. Let me write it in 1 over. Sorry if you did the same mistake I did. Okay, I want the limit as h goes to 0 of the dq. The limit of the slope of the secant line, that is what I want to figure out. And we're going to figure out what that is, and we're going to write that answer right there. And again, like I said, the reason I'm jumping around a lot here, and I know it's very inconvenient for you guys to jump around in the notes, is because the way this is organized in the notes is they have a whole bunch of functions we're going to do this for. So the next function is square root of x, and then the function after that is going to be 1 over x. And in the notes, they do the first row. They do all of the functions in the first row, and then they move on. But I want to show you guys the payoff. We did the x squared function. I want to show you the payoff of calculating these slopes of the tangent line. So that's what I want to get to. Okay, so we're going to calculate the slope. That involves doing a limit. And we're going to do that limit on a page coming up. It's going to be way into the future. So I apologize for all the flipping you have to do. It's here on page 452. Exercise 204 revisited. That's where we are. And I can screenshot the old one, yes. So if you're flipping, flip to page 452 while I go back and screenshot the old one. Here we go. This is the table. Okay. There's the table that we're doing. And we want to do the actual limit on page 452. So apologies for all the flipping, but I really want to show you guys the point of doing all these calculations. What's the point of all the algebra? It's going to let us calculate something that the Greeks could not figure out. All right. We're going to do part B. Part B says, use the answer to calculate the slope at x equals 1. That's exactly what I want to do. The slope of the tangent line at x equals 1 for the function f of x equals x squared. So we're going to do part B first. Part B says, please find the slope. And the formula is that the slope of the tangent line, at x equals 1 is the limit as h goes to 0 of the dq. Right? You take the limit of the slope of the secant lines, and when that limit exists, that's the slope of the tangent line. The secant lines are getting closer and closer to the tangent line. That's what we're doing. And if you want to be extra crystal clear, the dq at x equals 1, right? Because we're doing the value at x equals 1, so we plug in x equals 1. So this is the limit. H goes to 0, and the formula, based on the dq that we calculated, the first row of our table, is 2 times x plus 1 is 2 times 1, not plus 1, plus h. So we're doing the limit as h goes to 0 of 2 times 1 plus h. And this is already a very nice limit to do, because we've done all the work of simplifying the dq so that it's not a 0 over 0. We've already done all the work, all the hard work of calculating this limit. Right now, this limit is a just plug-in limit. It's 2 plus h. 2 plus h. What could be simpler than 2 plus h? This is a just plug-in limit. Just plug in, because we already did the work of making the 0 over 0 go away. And in this case, it's 2 plus h. You plug in h equals 0, you get 2 plus 0. The limit is 2 plus 0. 2 coming from the 2, h goes to 0, h becomes 0. 2 plus 0, so the answer is 2. The slope of the tangent line at x equals 1, according to our calculations, by doing the limit with algebra, we got 2. We got 2. Okay. And we can demonstrate that with Desmos if you want. This is something we've seen before. The slope here, we're saying in the limit that this gets really, really close to 1, the slope here is getting close to 2. So I can't make it actually 2 on Desmos. Desmos will freak out. Oh, apparently not. Oh. I thought Desmos would freak out. Oh, okay, look, there you go. It just doesn't have enough decimal places. If you make it really equal, boom, it's undefined. So Desmos thinks it's undefined because Desmos doesn't know how to do algebra. Desmos is still thinking 0 divided by 0. But we got around the algebra, we did the limit, and we figured out that it's approaching 2. We figured out that the actual slope should be 2. And that is why the equation 2 has a slope of 2 at the end here, just like this. Okay, so we figured out it's approaching this red line with slope 2, even though you can't figure out exactly what happens at h equals 0. You can take the limit as h goes to 0, and that's all fine. Okay, so that's what we've done. And I'm going to go back and fill in what we just did in a second. No, actually, I won't do that. I'm going to do part A first, and then we'll fill in multiple things at once. But this is a great time to stop and ask questions. Because there's a lot of different things going on, right? There's the slope of the secant line, the slope of the tangent line, all these different interrelated things. It's easy to get mixed up. Please ask me if something is unclear. Yeah? Yeah. Yeah, so how did I know I was supposed to do the limit as h goes to 0? Yes, so the way we have things set up, we said the definition was we're doing the secant line from x to x plus h. And so we always want to do the limit of the secant line as the 2 points get close together, and they both get really close to the point we're looking at. And because we said one of them was at x and the other one is x plus h, that means we want the h value to go to 0. You could do a different setup where you have a different label for all of the variables, and then it would be something slightly different. But really this h goes to 0 comes from h equals the distance between points. Distance between points. So you can always set it up like this and it will always work. But if you open a random calculus textbook, maybe they used a different thing and they'll instead of writing h goes to 0, they will write b goes to x or something, or x goes to b. But they mean the same thing. It's just that they set it up differently. In our setup, it's always h goes to 0. Yeah, no, this is a great question, and it's good to see what it represents. This idea of the limit, this is the big idea, right? This is what the Greeks couldn't do. The Greeks could not figure out that you got to do the limit as h goes to 0. They were just talking about oh, you can never move, right? So this is the whole magic of the whole thing that makes calculus work, is that limit highlighted in yellow. Okay. Okay, we're going to do the same thing again, but instead of doing it at x equals 1, we're going to do it at an arbitrary value of x. So we're going to do the slope of the tangent line of the tangent at x, where x is any value. X is any value you want. So we did it at x equals 1, and it made perfect sense. Now we're going to do it at an arbitrary value of x. So if we plug in x equals 1 on whatever we get here in part A, then we should get the answer in part B. So again, it's going to be the limit as h goes to 0, and now it's the dq at x, right? There's not x equals 1. Just leave the x as an unknown variable, and just every time you see an x, just leave it. And it's going to be a very similar limit. It's the limit as h goes to 0 of 2 times x plus h. And that was the formula we had for the dq, was 2 times x plus h. So now we're doing the same kind of limit as before, and you just have to not get scared away. We have x's and h's, but the limit only is about the h's. So the x is some fixed number, like 1, for example, and the h is the thing that we are taking the limit as it goes to 0. And this limit is exactly the same as the limit we just did. It's a just plug-in limit. This is a JPI. We did all the hard work of canceling and simplifying the difference quotient already. We're left with just this nice thing where you can just plug in. So you get 2 times x plus 0. The h It's a limit where you can just plug in, the h becomes 0 to evaluate the limit, 2 times x. 2 times x. So it's the formula, the slope of the tangent line at any point x will be 2 times x. When x equals 1, it was 2, right? At x equals 1, the slope of the tangent line here, over here, the slope of the tangent line was 2, right? What about at x equals 3, right? We did that. That was the warm-up problem today. At x equals 3, let me put in 3. That is all the way over here. Now we're looking over here. What is the slope of this guy? So again, you have to do the limit. A minus. Okay. So this was the limit we had for the warm-up problem. It looked just like this. And we determined the answer was 6. And we had this line of slope 6. So the tangent line now, through x equals 3, is slope 6. Why is it slope 6? Well, we calculated it's always just 2 times whatever the x value is. So when x equals 1, it's 2. When x equals 3, it's 6. 2 times x, that will always give you the slope of the tangent line at x. This is a cool thing. Like, we worked really hard to do it at one point, but now we've just had the value everywhere. And if you use this, you can make all sorts of nice pictures. Here is the one that I like. So here is the function y equals x squared in blue. And I have told Desmos, always make the slope of the tangent line twice the x value. The slope of the tangent line, I just said it's always twice the x value. And if you cycle what the x values are, let's go from -2 to 2. And if you play it, it will just go and it'll loop around and you'll have this nice picture and it always hugs the line. And I think you can even drag it, which is a nice thing. You can take this point and you can drag it around the corner here. And Desmos knows, because I told it, always make the slope twice the value of x. You can make this nice thing. So we figured out the slope anywhere you want on the function. We know how to do this thing no matter where you are. And it feels really good. You like loop around. It's great. It's really exciting. I highly encourage you guys to try it out. Okay. So this thing, this idea of figuring out the slope as a function of where you are looking, figure out the value of the slope as a function of what x value you're looking at. This thing is called the derivative function. So what we actually did here, we found the slope of the tangent line at x. This is actually the same thing as the derivative function. Derivative function. And the derivative function means exactly this thing, the slope of the tangent line depending on what x value you're looking at. So we have proven that the derivative function for x squared is this new function 2x. The notation people use for this is f prime of x, f prime of x. And we have shown that f prime of x in this case is 2x. This is a new function. We started with the function x squared, we did work on it, and we got this new function 2x. This thing is called the derivative function. So the original question says, find the derivative. We just did that. That was part A. We found the derivative function. Let me freeze this for a sec if you're still copying. In your notes, the definition of the derivative function is all the way over here on page 438. And it just says the derivative function is this new function, and it's exactly what we did. It's the limit as h goes to 0 of the dq. And if you do that for any value of x, that gives you a new function that tells you the slope anywhere on the function. That's called the derivative function. Okay, let's go back and fill this in on our table. So we have our table on the page before. What have we done before? So before we did the limit of the dq at x equals 1, and we got the value 2. That was the first thing we did. The slope was 2 when x equals 1. And the slope in general, the slope of the tangent at any value of x, at any x, that was the limit of the dq. Just leave the x alone. And we got the value 2x for the function x squared. This thing is called, this is the thing that is called the derivative function, f prime of x, f prime of x. So f prime of x is the new function 2x. And calculus is basically, how can we use the derivative function? First of all, how can we calculate it? And how can we use it to learn stuff about the original function? So if you had a problem where you really needed to know something about x squared, you would calculate its derivative function 2x, and then you would use what you know about the function 2x, which is a nice line, to learn stuff about the original function. This will go in the picture, so we kind of saw that in Desmos. Let me show you the paper version of doing this in Desmos. That is all the way here on page 443. And again, I apologize for flipping around so much. Let me freeze that. I'm going to go back and freeze the table, but we're going to go to this page 443. So when you're ready, start flipping there. So let me freeze this. But the derivative function and the function are, they're very closely related, and you can learn stuff about one from the other. This is the whole point of calculus. So we learned that the derivative function is going to be the function f prime of x equals 2x. But you can, just like we figured out in Desmos, we had this funny dance going around with the slope of the tangent line, we can sort of see how the derivative function and the original function are related. So let me show you what that looks like. So for example, what is the value of the derivative function at this x value? So when x equals whatever it is, let's pretend this is x equals 4 over here. What is the value of the derivative function? Well, it's always the slope of the tangent line here. And this slope is a big positive number, big positive number. So the value of the derivative is something over here. It's a large positive number. What about if we get a little bit closer? What if we do an x value like that? Well, here, it's still positive. So the slope is still positive, but this is a small positive slope. Small positive slope. So this was a big positive slope. This is a small positive slope. And we draw the value of the slope, whatever the slope is, we draw that as the height of the derivative function. So the small positive number is something like this, right? What about, this is a very exciting point. What happens right at the vertex? We're right at x equals 0. Right at x equals 0, the tangent line to the parabola is a flat line. It is a flat line. And that flat line has slope 0. Slope 0. And if the slope is 0, that means the value of the derivative function is 0. So that's why the value is 0. You can keep doing this on the negative side, right? So you can do, over here, you can have a small negative slope. So this is a negative slope. It's going down, but it's not a really large value. So this is a small negative number like that. Okay? And we'll do one more point just to complete the pattern. What do you get all the way over here? This is a big negative slope, big negative slope. Okay, so it looks something like this. So the values of the derivative function, this f prime of x, tell you the slopes along the original function. And in this particular case, for the function x squared, these things line up perfectly to make a beautiful line. A beautiful line. I can't draw a beautiful line. Let me try. Oh, this keeps moving. So much pressure. And the beautiful line is f prime of x equals 2x. It's the line of slope 2. So wherever you want to know something about the original function, if you want to know the slope, how it's changing, you can look at this f prime of x and it will tell you. And okay, let me freeze this if you're still copying that down. Hopefully it was clear how I got the dots. In Desmos, you can also ask it, please plot the value of the derivative function, and it looks like this, right? And the point is, if you want to know the slope of the red line anywhere, you can read off the slope of the red line by looking at the height of the green line. So let me pause the animation and do an example. Let's pause the animation and let's do an example. Here it's saying, okay, that's a bad example. Everything's a coincidence. Let's do this point. Let's do x equals -1. At x equals -1, the slope of the tangent line there through that red dot is -2. How could I have read off the slope is -2? The value of the green function is -2, right there, -2. If I want to slide it over, what about, I don't know, all the way over here? Here at x equals -2, the value of the slope is -4. That's because the green function is equal to -4. So that green function, the derivative function, tells you the slopes of the original blue function, how they are changing as you move around. Okay. So that is the visual definition sort of the derivative. In the table, we also have the algebraic definition. Yeah, I'll go back up to the table now. This is the big idea of this chapter, is the derivative function. This guy is the MVP, the star of differential calculus, is this f prime. So far, what we did last class and this class is learn what the f prime means, where does it come from, what is the conceptual idea. Later, next week, we're going to learn how to calculate f prime really efficiently and how to use it for things. But this is a great time for conceptual questions. What does this f prime represent? Any questions or comments about that? What it is, how you do it. Okay, so the next thing in the notes, we're going to fill in, we're going to do exactly what we did for x squared, but we're going to do it for the square root of x function. So we're going to start by filling in what is the dq for square root of x, and then we're going to take the limit of the dq to find the derivative of square root of x. So that is in the next thing we're going to do, and that is exercise 206. Determine and simplify the difference quotient for square root of x. And the dq is always, this is on page 434 by the way, the dq is always this ratio, f of x plus h minus f of x divided by h. That's what it always is. It's always this nasty 0 over 0 thing. In this case, that is the square root of x plus h minus the square root of x divided by h. And this is a 0 over 0 involving square roots. And we did an example in class. There's an example on the practice midterm involving 0 over 0s with square roots. Your brain should start going, you're like, oh, I know what to do with this. I can simplify this to make the 0 over 0 go away. And that is what I'm asking you to do in Math1030. So in Math1030, if I can find it, here it is. In Math1030, please tell me what you think we should do to deal with this stupid square root of x plus h minus square root of x. It's a type 0 over 0. How do we make the 0 over 0-ness go away? We multiply by the blank. And I'll give you a minute to see if you can remember. What is the blank? Feel free to talk to your neighbors or look through your notes. How would you simplify this limit? Okay, so there's like 10 seconds left. Feel free to put in, I don't know, IDK, if you really are unsure. I'm just trying to see how many people know this trick that's coming up before I do it. Okay, let's take a look. What is the trick to make the 0 over 0 go away when you have a square root? People said the trick is to multiply by the rationalize. Okay, rationalize is actually also a right answer. That's what we're doing. To rationalize means to multiply by the I don't know, the h over h. So the correct answer is this one, conjugate. That is what I went with. Let me see if there are other interesting answers. Reciprocal difference, the conjugate is a kind of difference. So I think some people maybe know how to do it, but don't know the word. Okay, so we're going to multiply by something plus something. That is the conjugate. The conjugate is this thing. Instead of being this thing minus that other thing, it's going to be this thing plus the other thing. Square root of x plus h plus the square root of x divided by the square root of x plus h plus the square root of x. This is multiplied by the conjugate. By the conjugate. And this is exactly forcing a difference of squares to appear. In the previous problems, we just had a difference of squares and we knew how to do it. By multiplying by the conjugate, we are making a difference of squares appear out of thin air. Because now we have the square root of something minus something times the square root of the first something plus the second something. So this is now a difference of squares in reverse. And so you get the square root of x plus h all squared. That's just x plus h. You get the square root of x all squared. That's just x. And it's a difference of squares. So we get this divided by h. The other side is x plus h minus plus square root of x. So I just did a difference of squares to bring those two terms together. The whole point of multiplying by the conjugate is to make the difference of squares appear. And now we again have all the miracle cancellations like before. X minus x leaves us with an h on top. H divided by h times square root of x plus h plus square root of x. And the same miracle happens again, that the h's cancel. the h's cancel out. And you are left with the final answer, 1 over square root of x plus h plus the square root of x. 1 over square root of x plus h plus the square root of x. That is the simplified difference quotient for the function square root of x. And there's the whole calculation. I'll freeze that while I go to the table and fill it in. We have figured out that the difference quotient is 1 over the square root of x plus the square root of x plus h. Okay, maybe it was written in the opposite order, but that's what it is. So it involves x and h. It involves the 2 points. The next thing in the table is this guy, this entry. This entry is the slope of the tangent line at x equals 1. And if you know the difference quotient and you understand what we were doing, you should be able to use this and do one limit, a nice limit, the kind of limit that could be on the midterm, to figure out the value there. I'm going to set you guys loose in a second to do that. But are there any questions or comments before we do that? Okay, so I'm going to have you guys, what is the slope of the tangent line to the function square root of x at x equals 1? That is the value that is going to go in this box. It's the analog. Before the answer was 2, the slope was 2 for x squared. What is the slope for square root of x? And in Math1030, I would like you to answer. That's here. So for the function square root of x at x equals 1, the slope of the tangent line is what? And what is this called? What is the math notation for this value? Those are the 2 questions. And they're exactly that square in the table that I said. So take 2 minutes to try to do this, and I will then reveal the answer. 2 minutes. And it should involve doing a limit. I think that table is very helpful. Do I have that table up there? I do not. Let me get the table up there. Okay, there's like 30 seconds left. You had to do a limit. If you're a little rusty on limits, you haven't studied for the midterm yet, you might not be able to do it in time. Try to at least figure out what is the notation for this in the last few seconds. It's multiple choice. And you can leave this one, just put in a 7 if you ran out of time. Because we're almost out of time here, and I want to just take up this final answer. Okay, so once again, what are we doing is so far we've calculated the slope of the secant line. That's the dq. And this is just like the question we started the class with. It's this question. Here is the function square root of x in black. And we're calculating the secant line. We have a formula, the dq, that tells us for any value starting at x equals 1, where does this guy end up? And the question is, what is the slope getting close to? That will be the slope of the tangent line. So here it's like 0.41, 0.43, 0.44, 0.45, 0.47, 0.48, 0.49, 0.491, 93, 979, 98. Oh, undefined, right? This is the whole point, is that it's undefined, but we figured out a way to make it have a definition by doing the limit. So you can't plug in h equals 0 directly. You have to simplify and do the limit. Here's the slope from the other side, 0.51, 0.501. Hopefully you see what it's getting close to. It's getting close to the value. It's getting close to the value 0.5. How many people got 0.5? Oh, wow, that was great. A lot of people got it. 0.5 is the right answer. And you can see it from the picture, but you can also do it by doing the limit. And if you do the limit of this thing, you plug in x equals 1, and you do the limit as h goes to 0. that will be a just plug-in limit, and you should get the value 0.5, or 1/2. Let me write 1/2. So if you got that, really well done. Congratulations. And by the way, what is this thing called in general? The derivative function f prime of x tells you the slope at any x value. What are we doing here? Not 1/5. Oh my goodness. 1/2. Okay. The derivative function f prime of x is the value at any x value. What are we doing? It is f prime of 1, which again, most people got. So very good. Really well done, guys. This is f prime of 1. The slope of the tangent line at x equals 1 is f prime of 1. The value is 1/2. I'll go over the limit in more detail next time. We're also going to do the general formula over here, and then we're going to do it for 1 over x and some other things as well. Okay, see you guys on Friday. I'll be here for a few minutes if you have questions.